Hi guys, welcome back. Today we are going to look at the other section of circular motion, which is the vertical component of circular motion. Okay, so in year 12, we've basically got three main situations that could occur. All right, the first one is when you are traveling at the bottom of a dip, and the dip can be considered as part of a circle. So for example, like if you're driving in a car and you go down a hill, then you come back up, right? This hill, this valley, I guess I should say, could be considered as part of a circle like that, okay? And we're going to be considering the motion and the forces that are acting on the object when it's in this position here, right at the bottom, okay? So that's number one. Number two is the inverse of this. So if you're not traveling down through a valley, through a dip, you're actually traveling over a hump. So it's something like this. Okay, so there's a hill, and the car goes up the hill, and we're analyzing the motion and the forces at this position up here. Okay, and again, you can consider this hill to be part of some kind of circle. Okay, so when you're going over the hill, you're actually in circular motion. And then in number three, we're considering what happens when you are at the top of a loop-the-loop. So consider like a roller coaster going around a loop like this. Okay, so that's, a section of track. And you can imagine the cart on the roller coaster is somewhere here. Okay. And again, we're considering the forces acting at that position only. So there's three main situations that can happen, and they're described by the pictures that you see here. Okay, so let's analyze the first one, which is traveling through a dip. Okay, so let's draw a picture and just see what's going on with the forces there. So here's our dip, like that. Okay, and our object is down here. Let's talk about the forces. So I'm going to use some different colors here because things might get a bit confusing. Let's use green for the forces. So, all right, what forces are acting on this thing? Well, obviously there's gravity involved. Otherwise you wouldn't go down the dip, you just fly across. So we know at least there's gravity involved. Label that FG. Okay, what else is involved? Well, this object is in contact with the ground, so there must be some kind of normal force, some contact force, and that is perpendicular, remember, to the surface at which you're in contact with, okay? So there's a normal force acting directly upwards in that case, okay? And for the most part, we're going to be ignoring friction and resistive forces. So really, those are the only two forces that are acting on this object. Okay. Now think about it. This object is in circular motion. Okay, it's restricted to move in a circular path, or at least part of a circular path. Where would the center of that path be? Well, if you look at the previous slide, this would be the circular path. So the center of the circle would be directly above the object at that point in time. Okay, so the center of the circle is somewhere here. Now, if an object is in circular motion, which direction does the net force point? It points towards the center of the circle. So the net force is actually straight up when the object is in this position. Okay? Whoa, what's going on there? Okay, so the net force points directly upwards. And now you can set up a little coordinate system for yourself. So you can say that upwards is the positive direction. Left and right doesn't really matter in this case. And now if we're going to describe the net force, well, the net force, which is vertical, would just be the sum of all the vertical forces. Okay, so the sum of the vertical forces is the normal force, which points in the positive direction, minus the gravitational force, which points in the negative direction. Okay. And for an object in circular motion, you've got to remember that the net force is equal to m times v squared on r, where v squared on r is the centripetal acceleration of the object. Okay. And we can rearrange this equation if you like, and we can get that Fn, normal force, is equal to mv squared on r plus gravitational force. Okay, and notice that because we're adding a quantity to the gravitational force, overall this thing that we get is greater than the gravitational force. Okay, so have a look what we've got here. We've got the normal force is greater than the gravitational force. And if you've ever been in this situation where you're in a car traveling at the bottom of a hill and you're starting to go back up, you might recognize that you feel heavier. Okay, it feels like you've gained 20 kilos and it just feels really heavy at that point in the motion. And the reason for that is because the normal force, the force that you're feeling the ground or the seat of the car apply onto you, that is greater than the gravitational force acting on you. And normally in everyday life, those two things are equal. But in this case, the normal force is greater than what it normally is. And so you feel heavier. You feel the ground pushing on you a bit more. Okay? What else can we look at here? Well, if I know, let's say, okay, so not really anything else that we can look at here. It's more to do with the other two cases. So really, if you've got a case like this, the question can really only be asking something like, calculate the normal force, or calculate, because sometimes this is replaced with the word apparent weight. Okay, it's the weight that you feel, okay, the force that you are apparently feeling. And that's equivalent to saying the normal force. So the question might be, what is the apparent weight of the person, in this particular situation? And really all you've got to do is, if you've got the other quantities, you just work it out using the formula we've got here. Okay, mass, velocity, radius, that's it. That's all you really need. Okay. Otherwise, if they've given you the normal force, then they may ask you, what is the radius of this circular path, if they've told you the velocity as well, or what is the velocity they're traveling at, if you know all the other stuff that's there. Okay, but really that's it. That's all we can really analyze in this case. I think it's the simplest of the cases. But take away from this, the normal force is larger than the gravitational force in this situation. So you feel heavier at the bottom of the dip. And the reason that the normal force must be greater than the gravitational force is that because the net force is upwards, and the only way that that could be the case is if the normal force had a larger magnitude than the opposing gravitational force. Okay? Right, second situation is when you're traveling over a hump. So let's draw the picture again. Here is your hill that you're traveling over. And the hill, you've got to remember, forms part of a circular path, something like that. And your object is at the top of the hill there. All right, so again, let's look at the forces that are acting on our object at this point. Okay, so obviously you've got gravity pointing downwards. Okay, Fg. And you've got the normal force, the contact force between the object and the curve or the hill, and that points upwards. Here we go. Now again, think which direction the net force is pointing. Okay, where is the center of the circular path? Well, it's straight down, somewhere here. Okay, so the net force, because the object is in circular motion, the net force must point down. Okay, at least at this moment in time. All right, so that means we can write, or we can set up our coordinate system so that down is the positive direction. Okay, again, we like to make the positive direction whichever direction the net force is pointing. Okay, that tends to be the simplest way to set up your problems. And now, if we try and go ahead and calculate the net force, well, because the net force is vertical, we just add up all the vertical forces. We sum the vertical forces. And because gravity is now pointing in the positive direction, we're going to be doing force of gravity minus the normal force, which points in the negative direction. Okay? And again, what is the net force equal to for an object in circular motion? mv squared on r. Okay? So we've got this little relationship here. Now, some things that we can analyze, okay? So, I mean, again, you can rearrange and calculate the normal force if you like. So all you're going to do there is swap the normal force and mv squared on r, and you'll get normal force is gravitational force minus mv squared on r. And you'll notice that because you're subtracting a quantity from the gravitational force, that overall the normal force is less than Fg, okay? So again, if you've ever been in this kind of situation, you might recognize that you feel lighter at the top of a hill like that, okay? And the reason, just like you feel heavier at the bottom of a dip, is because the normal force is less than what you're used to experiencing the normal force being, okay? Normally, the normal force and gravitational force are equal to each other when you're just walking along on the ground. But in this case, the normal force is less than the gravitational force, so it's less than what you're used to. So it feels like the ground is pushing on you less, so you feel lighter. Okay, again, that's called apparent weight. Okay, what else can we analyze? Okay, well, there's another really important thing going on in this situation. Imagine you're in a car, you're driving over a hill. If you're going too fast, what's going to happen is you go up the side of the hill and you'll just leave the track and you'll fly off into space and get some airtime, all right? So there's some kind of maximum speed that if you were to exceed that, you'd fly off the hill, okay? So there's some kind of Vmax. And so we say if you're traveling too quickly, then you'll leave the track, okay? Which implies that there is a maximum speed at which you can go over this curve. All right, now what does it mean to leave the track? If you're not in contact with the track, is there a normal force acting on you? No, okay, so the point at which you leave the track is the point at which the normal force becomes zero, okay? So what we can say is that this maximum velocity occurs just when you leave the track, okay? If you go any faster, then you'll definitely leave the track, all right? So this is like the tipping point. So Vmax occurs when the normal force is equal to zero, okay? Because that means you've left the track. You're going too fast, all right? And so that gives us a way to calculate Vmax, okay? Because if we're talking about, if we just use this net force equation that we've developed here, what we can say is then the net force is equal to gravitational force minus zero, because the net normal force is gone. Okay, so there is no normal force anymore, and so the net force is purely provided by the gravitational force. And again, in circular motion, the net force is equal to mv squared on r. Okay, only difference is now we're talking about Vmax, the maximum speed that you can take this hill without leaving it. All right. And you'll notice if we do some rearranging, okay, Fg, gravitational force, is mg. And we can cancel out m on both sides there and solve for Vmax. Okay, and we get Vmax is equal to the square root of g times r. Okay, so if you are going faster than Vmax, then you will leave the track. If you're going slower than Vmax, you will stay on the track. And if you're going at Vmax, then for a fraction of a second, for the smallest time interval possible, your normal force at that point is going to be zero. Okay? So there we go. Right, the last situation, loop the loop. Okay, now we're going to analyze this. It's very, very similar to what's going on here. There's a lot of the same ideas that are expressed as in a loop as there is here, but let's draw a picture anyway. So here's our loop the loop. Okay, and we're analyzing what's going on at the top of the loop. All right, so let's draw our forces in. What's acting? Well, we've got downwards force, gravity. I think I've swapped the colors around. Who cares? Okay, gravity is downwards. But if you're at this point on the track, the point of contact is above the object. So the normal force must be pointing downwards. Okay, so the normal force is also pointing downwards. And again, you've got to think, where's the center of the circle? In this case, the center of the circle is right there. So the net force must point downwards as well. Okay, and there we go. That's F net there. All right, and that gives us a way to set up a coordinate system because we know that the net force is down. So let's say down is positive. And let's write up an equation describing the net force. Okay, now the net force is just the sum of the forces, in this case the sum of the vertical forces. And notice both the normal force and the gravitational force are pointing in the positive direction. So the net force is just equal to Fg plus Fn in this case. And again, for an object in circular motion, the net force is equal to mv squared on r. Okay, again, you can rearrange this and calculate Fn. We're not going to talk about feeling heavier or lighter here, but we can calculate Fn if we wanted to. So Fn is just equal to mv squared on r minus Fg. Okay. Now, you've got to try and imagine the situation. Okay, if you're going too slowly, what's going to happen is you're going to go up the side of the ramp and then just sort of fall over and hit the ground. Okay. So if you're going too slowly, you're going to fall. All right. So if you travel too slow, right, you leave the track. Just like in the previous situation, if you're going too fast, you leave the track. Okay, and in this situation, it implies that there is some minimum speed that you need to be traveling to make it all the way around. Okay, otherwise, if you're traveling less than that speed, you'll leave the track. Now again, what does it mean to leave the track? Well, if you've left the track, you're not in contact with it, which means there's no normal force. So the normal force is equal to 0 in that case. Okay, and our job is to try and work out when that happens, what speed that is going to be. Okay, so V min occurs when the normal force has just turned into a 0. Okay, and then at that point, if you go any slower than that, then you'll definitely leave the track for a considerable amount of time. Okay, so again, we just analyze it in terms of the net force, and we can say, therefore, the net force is just going to be equal to Fg, okay, because the normal force is 0, the only thing contributing to the net force is gravity. And again, for an object in circular motion, the net force is equal to mv squared on r. Okay, and that's V min. Okay, and again, you can rearrange it, do whatever you like, and you'll notice that the minimum speed will be given by square root of g times r. Okay, so there we go. Okay, you've got 3 situations. We've got traveling through a dip. We've got traveling over a hump, where you've got some kind of maximum speed you can travel before you leave the hump. And you're traveling over a loop-the-loop. At the top of the loop, there's some kind of minimum speed you need in order to make it all the way around. Okay, and we've got ways of calculating those things. Okay, so let's have a break there, and we'll see you in the next video.